Welcome everyone to our today's webinar. Again, it's a webinar on the DYNAmore Express series, and actually this is the first time we do it in a different way. I mean, as you may remember, usually we do it through WebEx. This time is the first time we're going to do it through Vimeo as a live stream. And so things are slightly different today. So everyone who's joining right now, I mean, you can only ask questions through the chat box. So if you have questions, feel free to post them in the chat. And either I'm going to try to answer them, or maybe I'm going to forward the questions to the speakers later on. And that way, I think you're able to answer all your questions. Also note that the video is going to be recorded, and you can find later on the recording on YouTube later on. So with that being said, I think I'm going to introduce the speakers today. Today we have a webinar on an update status of LS-OPT, and the speakers today is Mr. Nielen Standard, and help me please, Anirban, Basudhar, both are developers of LS-OPT, and they give you today an update on LS-OPT. Wait, I need to now.
Okay.
Give me a second.
Okay, thank you. Thank you.
Okay, sure. Okay, and yeah, wait, sorry. Now you can start. Okay, so now it's your turn and you speak and I'm listening.
Okay. Thank you, Mike, for the introduction. I'm Anirban Basudhar from Ansys, like Mike said, giving this presentation along with my colleague Nielen Standard. So in this presentation, I will be first giving brief overview of the capabilities of LS-OPT, followed by I'll talk about the current production features in LS-OPT 7.0, which has been in production for about a year. Nielen will then talk about a few of those features as well as the upcoming version, which is 2022 R1. He'll talk a bit about the future versioning and licensing of LS-OPT, as well as the upcoming features related to extraction of results, as well as some new introductions to the interface, as well as metamodeling. Followed by that, I will finish by talking about some of the future developments related to 2022 and beyond, and give a summary of all the features. So this is an broad overview of LS-OPT capabilities. As you all know, LS-OPT is process integration and optimization software, which has a lot of flexibility in how a process can be defined. It can have multiple stages or solvers, such as LS-DYNA, as well as some solvers, including user-defined solvers. It can have multiple samplings, which can sometimes handle multiple disciplines, as well as it allows multi-level process to be defined. And all this together, LS-OPT gives you a lot of flexibility in terms of what kind of process can be defined and eventually optimized. The methods in LS-OPT are broadly based on direct simulations, based on metamodeling or classification. So in direct simulation, basically we perform for instance finite element analysis at all the sample points. In the second one, which is the metamodeling method, most of you should be familiar with. We perform few simulations, and we can compute the finite element results and those followed by approximation of the response functions using a metamodel. In the third case, the idea is to again perform a few simulations, a few finite element simulations. And in this case, instead of trying to approximate the values of the responses, we try to classify the response as feasible or infeasible. For instance, this can be used for defining the constraint boundaries of a design problem. And the classifier that we have in LS-OPT is support vector machines. Now, LS-OPT can be used for optimization, which can be multidisciplinary optimization as well as So in the past, Monte Carlo task was restricted to a single iteration in LS-OPT. Now you are able to do this criteria is fulfilled. So this is how the interface looks like. You have this new sequential option under strategy. Now, the sequential Monte Carlo analysis can be done in two ways. The samples can either be added in a space filling way or in an adaptive way. So we have two examples here. At the top, we have sequentially added samples that are space filling. So you can see that going from iteration 1, 5 to 15, the density of the samples increases, but it stays In the past, adaptive sampling in LS-OPT was restricted to the to optimization using the sequential RSM method, in which we started with the entire design space to begin with, and then as the iterations proceeded, the next region of interest was defined around the previous optimum solution. and the size of this region of interest was adjusted going from one iteration to another. However, this type of adaptive sampling was restricted to optimization alone. No special emphasis was given to reliability or reliability-based optimization. So now, with this new kind of adaptive sampling, which we refer to as explicit design space decomposition, and it is based on classifiers, we are able to define sampling regions that are irregular. They don't necessarily have to be a box. They can be any irregular shape. They can be disjoint in this design space. And they don't really depend on the optimum location. Instead, they focus on the constraint boundaries. So the adaptive sampling is now more general in nature, and it can be adapted to what kind of problem you have. So for optimization problems, you would have a certain type of EDSD sampling constraint. And for reliability-based problems, you can have a different type of EDSD sampling constraints. So this feature is available as a way to define constraints during your sampling. So this is how the sampling dialog looks like for EDSD sampling constraints. In order to define this, first you need to define a classifier, and then that list of classifiers appears on the right. And once you have that list, you can select this classifier to define the conditions for your sampling constraint. So the basic idea here is you build a classifier, which in this diagram is this blue curve. And once you have that classifier, the user can specify a lower and upper bound for the SVM boundary. SVM is the classifier type that is used. And the user defines the lower and upper bounds for SVM. At the blue curve, which is the classifier decision boundary, SVM value is equal to 0. If the user doesn't define, then of course there is a default value for the lower and upper bounds, which is -1 and +1. And these values are given based on certain characteristics of SVM, basically. Now, in general, what should be the lower and upper bound really depends on a particular problem. I mean, there is certain logic behind -1 and +1, but we don't exactly know what would be the optimum value to select for sampling for a particular problem to make it more global or less local, the placing of samples. So in order to overcome this issue, it is possible to randomize the lower and upper bounds also using this randomize button checkbox. And when you do that, these lower bounds and upper bounds are randomly selected within the range that is specified as the minimum and maximum range. Also, it is possible to deactivate the sampling constraint for certain samples. So for instance, if you are selecting 10 samples for an iteration, it is not necessary that all 10 have to satisfy this sampling constraint condition. This is done in order to preserve the global nature of the search. So some samples are allowed to be anywhere in the space so that you can explore the entire space. Another thing that we added in 7.0 was distribution fitting. So in 7.0, we have an ability to fit normal and Weibull distributions to observed data. So the user can simply give a text file with the observation data, a list of observed values, and then LS-OPT automatically fits a Weibull or normal distribution to that data. This way, the user does not need to pre-process the data to determine the distribution parameters. The sensitivity analysis features were also enhanced in 7.0. Earlier, in previous versions, sensitivity analysis was available for responses, for scalar responses, basically. But in 7.0, it is also available for multi-point responses or spatial data. And this is possible by the use of proper orthogonal decomposition or PCA-based approach. The display is very much similar to what you had before for scalar responses. But instead of scalar responses, here we are looking at the sensitivity of multi-point responses with respect to the design parameters. A lot of additions were also made in terms of material calibration, as well as some flexibility of the LS-OPT interface. And Nielen will be talking about those changes.
Hello, yes. My name is Nielen Stander, and I'll be talking about some of these topics like this one, the material calibration, as well as introduce also the new version, which is being released in January of next year. So for those of you who are familiar with LS-OPT, a lot of the use of LS-OPT is for material calibration. And so maybe I can I just want to refer to a summary. Anirban, can you just move to the next slide? So this is a summary of what we call similarity measures available in LS-OPT. What they are basically is a method where you can compare the computational result, for instance, a history or a crossplot of histories with the test result. In order to do that, there are certain similarity measures that can be applied. And so over the years, we've developed these according to the deficiencies that we picked up from applications. So this is a list, just a summary of what we had, what was implemented in the past. And then at the bottom, there's a new method that we implemented in version 7.0. And as you can see, we tried to address the deficiencies as we went along. There's the problem of hysteresis, for instance, in the curve, when you have loading and unloading case. There's also the case of noise, for instance. One of the problems is, and we managed to address those with some of the methods that we implemented up to I think 6.0 perhaps, or 6.1. But there was one issue that remained, and that was the one of partial curves, where you have one curve which is significantly longer than the other. So if you can switch to the previous slide again. So we have, for instance, if you look at the figure on the left, you can see there's the blue curve, which is a short target curve. So that's what you're aiming for. And then there's the green curve with the dots. And the idea is to calibrate the material so that those two curves can meet up. But they are partial curves. And so the method that we implemented earlier, which is called the dynamic time warping method, connects points on the test curve with points on the computed curve. But at the ends, there's a problem because you get this, what we call fanning of the path, where you have only a single point, for instance, in this case, on the test curve, on the beginning and the end of the test curve, the blue curve, which connect to several points on the computed curve. And so we implemented a method whereby we could eliminate the fanning. And so if you look at on the top right, you can see the effect of that. What you see there is a result of using the so-called Gizmo LS-DYNA material model. It typically results, it's a failure model. So it can model the fracture. For instance, if you have a tensile test, you get fracture. And so the two parts of the coupon that you're testing can separate. And so you get this noisy sort of bass vibration that you can see there on that figure on the left. And so the idea is, but the test points in this case are those black crosses that you can see. There's a purple line that comes down. That's really the test, but only up to the last black cross, which is somewhere there in the middle. And so if we apply this method now, you can see that we're comparing the test curve. If you look on the right, in the top right there, you can see that the test curve is now roughly equivalent in its geometry to the computed curves. And so we've truncated the computed curves using this the method which we call partial dynamic time warping. So we ran this as an optimization problem, and you can see there is a difference. Actually, the standard DTW method didn't come out too badly. You can see after 20 iterations, the curve match is pretty good. But there is an improvement, and even in fewer iterations, that the partial dynamic time warping method is able to give a very accurate result. So let's move 2 slides on. We also in version 7 implemented process management, and this was just a tool so that users could set up the total problem, but leave out certain parts of it that will not be used during the optimization run. And we implemented this for both cases or samplings and also for the individual stages. So these are just 2 simple examples just to show how they can be deactivated. So they'll grayed out. It doesn't mean that the one on the right actually would work, but it is possible if, for instance, you have 2 cases, but you only want to run one of them to just deactivate the particular case. So this provides more flexibility for maybe a team, maybe just 2 people working on the same problem, and maybe one person is analyzing a particular, it's a noise and vibration NVH case, and the other one is analyzing a crash case. Or something of that nature, so that they can test within the same framework. Those can be tested individually. So it is a type of debugging tool. So let's just move on to the next. And then we also, I'll just summarize, we redesigned and re-implemented the job scheduler completely. The previous job scheduler was fairly limited. For instance, it only had a limit of 300 parallel jobs that it could run. That was kind of a system limitation. So we just eliminated that problem. And then we also provide SSH support now. And so this is something which is well understood by the IT staff typically, and I think used quite often. Then we also simplified. Previously we had a system which we called a black box, which was really designed to deal with security in the system, like firewall type of situations, and this is now and previously the user had to set up a script, so we've made this much easier. There's a graphical user interface now how to set this up, and you could, for instance, specify also user-defined termination criteria in the GUI, such as return codes maybe from your solver. The one that we typically use is the more normal line in the standard output, file existence, a particular line which needs to be looked for in the file, etc. There's some other minor changes, for instance, the port range. And this is all in the graphic user interface. And this job scheduler, I'm not quite sure where it's used. I think it's now also used in LS Task. It's very similar to the one that was previously in LS-Run, and I was maybe partially adapted from that. And I think there's a potential that LS-Form will also use that, perhaps through LS-Run. I'm not quite sure about that. Yeah, but so that's the job schedule. So allow me to move on now to LS-OPT Pro 2022, which is our next version. So you'll see that the version naming will change. And so we will have the year and then two revisions. One will be at the beginning of the year and the other one sort of mid-year, the R2 version. And LS Pro becomes a licensed code. So, and this is part of then a three-tiered licensing system together with the OptiSlang code, which is the other Ansys optimization code, who will have a premium and enterprise versions. So what we've done is we've exchanged some in order to provide a natural progression for people who want to use LS-OPT Pro and then graduate to OptiSlang. We've exchanged some of the technologies. For instance, from OptiSlang, we imported a method which is called the method of optimal prognosis, which allows for automatic selection of metamodels. And to OptiSlang, we provide the DYNA interface and also some of the LS-OPT metamodels, as well as classification, which Anirban just spoke about earlier, which is now also transferred through the extractor. But I'll say a little bit more about that in future slide. So the first version is being released in January of 2022. I have a few details here about features, but they are also in the future in this next few slides. So I'll just talk about it then. There's basically the MOP version, which is a metamodel selection. There's Cora, which is a feature used in the automotive industry for crash barriers. There's some element interpolation, and then a big feature is also the LS Reader integration. And Anirban will also speak about the future research. So let's move on to then the next release. So the first thing we did was we provided, as you probably know, that the extractor has always been a standalone executable, and what we've done now is made this available to anybody who wants to use not only extracting LS-DYNA results from the D3 plot and the bin-out files, but also for other applications, such as those in automotive crash, which are typically the injury criteria. There's also some other basic operations or operators on the LS-DYNA results, the cross plots, the integration, some filtering techniques is all included into that. And what we've also done is we've implemented LS Reader, which is an LS Prepost development, which is also now in LS Prepost, as well as LS Task. That's the core extractor or core extraction library, I would say, for all LS-DYNA results. So that was implemented in LS-OPT and now supported by the LS Prepost group. So this means that all updates to the LS-DYNA database is automatically supported. So it also allows us to expand the types of hasn't had result extraction for acoustics, for CFD, for thermal analysis, etc. But this will also now become available, probably in the 2022 R2, the mid-year release for next year. But this is a methodology whereby optical results can be mapped to the finite element model, and then the difference in the optical results from a digital image correlation test can then be compared to the computational results. So we use a point mapping system to map a digital point on, or a test point on mesh. And in the past, it was quite simple. Actually, we had nodal mapping, and then we had mapping to the center of the solid, and also the mapping to a quadrilateral shell elements. But we can now include any type of element, the ones that you see here, tetrahedra, pentahedra, and also the triangle, because those are typically, especially in mesh generators, you find them often find a mix of elements. So, for instance, in shells, triangles are used to fill in certain areas, or in solids, tetrahedra might be used to either generate the entire mesh or also fill in certain areas. So LS-OPT in this next version then interpolates a point exactly within each element. So we use a reverse interpolation algorithm to then determine the result at any particular point of any of these elements that I'm showing here. So next slide. The metamodel of optimal prognosis. I'm not going to talk much about it here, except to explain that it's a metamodel. User has to select, and then there's always that decision that has to be made. So what we've adopted from the OptiSlant code is the metamodel of optimal prognosis, which is a single metamodel which actually does the selection internally. And so currently, we've added that on as an extra metamodel, and currently it supports linear, quadratic, and kriging, but we'll also in the R2 version, which is June of 2020, comprehensive. Next slide. And so we did two examples here. There's a small one. This is two variable, the so-called torus model, and then there's also a truck model with 22 variables. And you can see in the columns there, well, on the left are some of the responses. These are intrusions, I think mostly. And what we did is we did 200 points we used to construct a metamodel, and 800 checkpoint. So they just used for calculating errors. And then, so what's plotted in what's tabulated here are the actual root mean squared errors of those checkpoints. And you can see the MOP is marginally better than the current metamodels in LS-OPT, whereas the other column MOP is the new selection methodology. And so you can see it does marginally better on some of those or most of those responses. But if you look at the next example, on the next slide, this is a truck with a frontal impact in which we've introduced 22 variables. You can see here that in this case, the current metamodels, the neural network metamodel, the radial basis function metamodel is sort of marginally, if you look at compare the numbers, they're marginally better than the MOP system. So this means, I think all this really tells us is that it does make sense to combine all the LS-OPT metamodels also into the MOP system, so that the best ones can be selected automatically, and so it frees the user from having to make that selection. The next slide. So the Cora interface, that's the last feature that I will talk about, and that's just a feature for ISO rating of dummies and barriers used, I think, mostly in the automotive. Well, we worked with an automotive company to do this development. So what we provide here is within the process flow is an additional stage type, which is the Cora stage type, and so that allows the user to rate the performance of impact of dummies and barriers. I mean, the rating is just a weighted sum of the measures from the different approaches. So so this is a separate stage, and you can see that there's a GUI on the right. So the user doesn't have, in the past, what users did, they wrote scripts and incorporated this as perhaps a user type of stage, whereas now all of this is incorporated, and so the scripting, if any, I don't think there's any scripting necessary here, is addressed or is supported by the graphical user interface. I don't know, Anirban, before we move on, is there something more you wanted to say about Cora?
Yeah, no, that is fine. So the only thing to add is that the ratings are basically available for the total entire problem or for a particular load cases and sub load cases as well. And then there are different types of ratings you can see in the GUI here that are available, such as the corridor measure, phase measure. The people who are using Core are probably familiar with those types of measures.
Okay, so I think
yeah,
I think you move on from here.
Right. Yeah. So moving ahead, I'll be talking about some of the developments that are some of them are already underway at a quite advanced stage. For the future versions starting 2022 R2 and beyond. So one of the things that we are working on is reduced order modeling. And similar to meta modeling, here we try to basically capture the behavior of a finite element model. And instead of trying to predict scalar values, what meta models do usually in LS-OPT, here we try to predict the entire system behavior, meaning we try to predict histories, multi-point responses, or multi-point histories. So the basic idea is we start with a set of samples. We run some simulations. So we see some acceleration histories in this case. So I'm demonstrating this for single point histories. So once we have those histories, or they can be multi-point responses or histories as well, we build a reduced order model, which is based on PCA or proper orthogonal decomposition, and as well as meta models. So we get a reduced order model, which looks like this expansion basically. So we capture a few important modes from the behavior of the model, and the final system behavior is represented by those few modes. So MS does not represent all the modes. Typically, it is a very small fraction of all the modes. So you have only a few terms in this summation. And these eigenvectors V's are obtained using PCA or POD. And the alphas, which are the coefficients, a function of the parameters in the problem, they are approximated using meta models. So for any new point, once we have the reduced order model trained, for any new point or any new combination of P, we can feed it into the ROM, and that gives us the predicted history. Now, we have already implemented this basic methodology based on a combination of metamodels and proper orthogonal decomposition into LS-OPT. It is not available yet. It's targeted to be available in 2022 R2, which is mid of next year. There is still some work that we are trying to do in order to increase the accuracy of the estimate. So one of the ways we are trying to address this is by trying to partition the model into subregions so that the highly nonlinear regions, such as in this case, that would be the region where the ball impacts, we are trying to automatically partition the space into nonlinear versus relatively linear regions so that particular emphasis can be given to the modes important for those cases. So the idea is to divide it into a general any number of regions, basically, which would be automatically determined by LS-OPT. And then LS-OPT will build a separate ROM for each of those subregions. Because the idea is that if the behavior is highly nonlinear in a particular region of the space, then those may not have the same important eigenvectors as the regions which are not so nonlinear. So there is a need to treat them separately. Also in the future, which probably won't be part of 2022 R2, but we are also looking at deep neural networks to predict the system behavior as well. Another feature which is also at an advanced stage of implementation is a new method for multi-objective optimization, which is an adaptive method based on classification. So until now, in LS-OPT, we have NSGA2 based multi-objective optimization, which can either be direct or it can be using metamodel-based approaches. However, the current method is metamodel-based method is not really adaptive. In the sense that the samples are added sequentially, but they are added in a space-filling manner in order to get the next Pareto optimal front. So the idea here is to have an adaptive method to be able to predict the Pareto optimal front in a much more efficient and accurate manner. So if you consider a design space that has a few samples to begin with, let's say, if we evaluate them, we come to know that a lot of those samples are dominated and they cannot be Pareto optimal solutions. These red ones, let's say they are dominated, so they won't be Pareto optimal. Now, if we consider a new point, which is which has not been evaluated. So if we try to think intuitively in this case, whether this point is likely to be a Pareto optimal solution or not, the answer is probably no, because it is surrounded by a lot of dominated points, and therefore it is very likely that this point will also be dominated. So if we can define a region in the design space where we can say that this is the region that is likely to be non-dominated or potentially Pareto optimal, then we can target our resources in that region instead of trying to sample everywhere in the space, which might lead to a lot of wasted simulation.
And this is possible by treating this problem as a classification problem. So the basic idea here is you start with a few samples. For those samples, you know which ones are dominated, which ones are non-dominated. And then we have introduced a new type of classifier that constructs a decision boundary based on the domination status. So this dashed boundary here separates the dominated points and the non-dominated points. And once we have that, then I talked about the classifier-based sampling constraint earlier. This decision boundary can be used to adaptively sample so that you are not doing a lot of sampling in the white regions which are not expected to be non-dominated or Pareto optimal. This method is has been patented in-house, and right now most of the method has already been implemented. There are a few couple of more steps of the original algorithm that still need to be implemented. However, it has already been shown to, even in its current status, it has already been shown to outperform the existing methods. So the results here are from the original method, which will be implemented in 2022 R2. And here you can see two examples. At the top here, we have a standard ZDT3 example with 30 design parameters. On the left, we have the result from NSGA2. And on the right, we have the AMU result, which is the classifier-based adaptive multi-objective optimization method. And clearly, you can see that the one on the right is much better, as the actual solution here is represented by those brown points. And you can see that NSGA2 here misses two of the Pareto optimal front subregions, whereas AMU is able to predict all of them accurately. For this 7-variable truck problem also, which is a tolerance optimization problem, we can see the comparison between the classifier-based adaptive method and NSGA2. So in this case, the black plus signs, they represent the classifier-based adaptive solution, and the green and red points, they represent Pareto optimal fronts using NSGA2 at 30th iteration, which is the same as the black points, as well as the 50th iteration in red using NSGA2. So you can see that even after 50th iteration, the NSGA2 solution cannot match the AMU solution received at 30 iterations, which is much better in terms of the spread, and for the most part outperforms the Pareto optimal front from NSGA2. So, so we expect to have this method in 2022 R2. One thing I should also mention actually about the classifiers. So in this case, it has an application to multi-objective optimization, but in general, it is also useful for problems that have binary or discontinuous responses, because for those type of problems, it may be difficult to construct meta models because of the discontinuity, but classification-based approaches do not have an issue regarding those problems either. Another thing that we are working for the next mid-year release is point set registration. And there are two types of applications here. One is based on rigid point set registration, and the second one is based on non-rigid point set registration. So the first one is related to shape optimization of a parameterized LS-DYNA model, for instance. When you try to match it to a point set. For instance, if you have a medical imaging data, so you have a MRI image, And then you have LS-DYNA model of a body type, let's say, such as a heart. Then you can use the point set rigid point set registration to match the LS-DYNA model to that point set. The second type of application can be, for instance, in the case of mode tracking. If there is remeshing, then the model assurance criteria used for mode tracking does not work, because it relies on these vector operations where the eigenvectors have to be of equal length. But if there is remeshing, then these eigenvectors may not be of equal length. And even if they are of equal length, sometimes the ordering can be changed, so you can't really do those operations. So in such cases, it is important to instead get a mapping between the original shape and the new shapes in order to be able to perform these operations. And point set registration can be helpful in such cases as well. So there are some other developments that are at their early stages, such as some developments for reliability, for instance, including the error of metamodels and classifiers into the probability of failure estimate. Also, we are going to work on some adaptive methods for reliability assessment. Some of the other features that we will be working on are metamodel formula for all types of metamodels. Currently, they are available only for polynomials and RBF. We plan to make it available for the other metamodel types as well. We are also working on a parallelized version of efficient global optimization. We have efficient global optimization based on kriging already available in LS-OPT. However, the parallelization that we have is not ideal, so we are working on a much more improved parallel version of the algorithm. Also, there are some DYNAstats improvements that we are working on. Now that we have sequential Monte Carlo analysis, it makes sense to have that extended to DYNAstats as well, for instance. So to conclude, a major change right now is the transition of LS-OPT into the licensed LS-OPT Pro product line, where it will be under a 3-tiered licensing system with OptiSlang. The first version of LS-OPT Pro would be in January, and that would be our 2022 R1. Old versions are of course still available. A major change in this upcoming version is the integration of LS-OPT Extractor to LS Reader. And this gives us a lot of flexibility in terms of adding new types of responses that are not yet available. Like Nielen said, we in the past did not have direct access to thermal, electromagnetic, CFD results, etc., using binary files. So those can be much more easily added now. Also, this gives us a more stable product because any changes to LS Reader, if there is a bug fix or there is an improvement, they will automatically be reflected in our extractor as well. So LS-OPT will always be up to date. In 2022 R1, metamodel of optimal prognosis has been added, which allows for LS-OPT to select the best model metamodel automatically, so that the user doesn't have to choose which metamodel to use. Some interface enhancements have also been added. For instance, the Cora interface has been added. Also, we are working on some technological improvement in the field of approximation as well as optimization and reliability, such as reduced order modeling, adaptive multi-objective optimization, as well as adaptive reliability methods. So with that, I would like to conclude this talk, and thank you all for your attention.
Okay, thank you. It was a very interesting talk and a lot of comprehensive information, I would say. So no one posted any question in the chat, but I have a quick one. Can you just explain the tier model of Ansys a little bit? What's Pro, Premium, and Enterprise? Do you have an idea? Can you comment on this a little bit? So why is LS-OPT, for instance, part of the Pro tier? Oh, okay, I'm muted. Okay, again, I have a short question. So no one posted a question in the chat so far, but I have a short question. Can you comment on the tier of Ansys? So what is the Pro tier? What is the Premium? What is the Enterprise? And why is LS-OPT part of the Pro? If I get it right, maybe I missed it before.
Nielen can
yeah, I can respond to that as far as I know. So the idea is to have 3 tiers in optimization. Now, currently, there's somewhat of a mismatch, and I think the idea is to have better integration between the codes. But so there's LS-OPT Pro, which is supposed to be an introductory version of optimization, and then there's 2 versions of OptiSlang, which is in some respects, I mean, there's an overlap between the 2. And so there's, in some respects, are more sophisticated in certain areas, whereas LS-OPT provides more sophistication in other areas. So at the moment, there's some integration between the 2 where we've exchanged technologies, and this is likely to continue to some degree wherever possible. But really, it is a more of a, I think, perhaps a 2-tier system where there is a differentiation between LS-OPT Pro, which is the same as the old LS-OPT in the sense that it has the same graphical user interface and the same features. But the 2 codes are just enhancing each other with the technological exchanges that we're making. So there's no real continuation, I think. But LS-OPT is at the bottom of that tier ladder. So will be the cheapest one as well.
Okay. But usually also the LST products or LSTC products used to be cheaper than the competitors, as far as I understood in many cases.
Yeah. Well, you know, LS-OPT was free in the past. I think the fee is fairly minimal. I don't know whether it has been announced. I think the big difference here is that OptiSlang was before the acquisition was a licensed product.
Yeah.
So they have an established customer base based on licensing, whereas LS-OPT was automatically licensed together with.
Actually, that was the beauty of the LS-DYNA product family. That's you buy one and you buy it one time and you get a lot of things for free, or not for free, but you get it because you already have the basic license, and that's it. Yeah.
You guess it because you already have a license. So yeah, perhaps I should add that the 2022 R1 license has licensing integrated with the code, but until 2022 R2 there's no charge. So users can try out the new version for free.
Okay, I think with that being said, I would somehow finalize this webinar. So by the way, sorry for the audio issues at the very beginning. You had some echo. I fixed it.